In this class, we're going to take a look at the graphs of functions. So when you first start working with functions, it's enough to be getting on with just to figure out what a function is, what it does, what you can do with it. And the graphs come a little later, but once you get into the graphs, it provides a visual on the function. It allows you to study the function in a more kind of visual way, and it just gives you insight into the function that you don't necessarily get just by looking at the algebra. So in this class, we want to figure out what even is the graph of a function. What does that mean? How do we construct the graph of a function from the algebra? And then to draw some general conclusions about the graphs of functions. So if you're going to be studying functions up to say pre-calculus, even calculus level, then it's a really great thing to get a good understanding of how the algebra and the graphs go together. It's a really powerful tool, and you probably will in the future end up spending quite a bit of time working with the graphs of functions. So we're going to start that journey in this class today, or if you've seen these before, maybe this will be a bit of a recap for you. So before we get to these examples, let's just consider what a function is. So we're taking a step back and then we'll work our way forward. So a function is just an input-output machine. You give the function an x value, that's the input. It gives you an f of x value, which is the output. So to take a simple example, if you had f of x equals 3x. So that's a function that says take your x value and multiply it by 3. That's what that function is doing. That's what the rule is. So if you were to put like the number, say 2 into the function to get f of 2, then that's just going to be 3 times 2, which is obviously 6. If you were to put 4 into the function, then that's going to be f of 4, 3 times 4 is 12. So these are the input values that we're putting in here, the x values, and these are the output values. So that's just what a function does. Now, how do we get from that to looking at the graphs of a function? Well, what we basically do is we say, well, how about if we pair these up, 2, 6, 4, 12, and then other potentially other numbers as well, and we consider those to be the coordinates on an xy axis, like on the Cartesian coordinate system. So that would be the point 2, 6 on the graph of that function, and this here would be the point 4, 12 also on the graph of that function. So if we were to go ahead and actually plot those points, so we've got the first point at 2, 6, so 2 along, 6 up. Let's just imagine that's going to be roughly there. And then the second point at 4, 12, so 4 along and then twice as high, so 12 up. That's going to be there. And then if we were to carry on and get more points, then we could just basically build up the graph of that function. Now this is what's called a linear function. We'll chat about the types of function later on. Linear functions just make, as the name suggests, straight line graphs. This is just a straight line, so therefore we only need 2 points to actually define the graph of that function. Some graphs are curvy, they make curves. Some are straight lines. It depends on the type of function. But the point for now is not to worry too much about the shape. The point is, how did we get here from here? So we just took the input and the output and made a coordinate, and we then plotted the coordinates. So this was a point 2, 6, and this was a point 4, 12. And that is what the graph of a function is. It's just a bunch of points. Generally, we don't need that many points. We need the key points, really. For a straight line graph, a linear function, which this one is as well, all that we need actually are 2 points, because if you've got 2 points, you just draw a line through them. If you have a more curved function like this, you can't draw every single point because there's infinitely many. You might want to know what these key points are. So it depends really on the function type as to how you're going to draw the graph, but the principle is the same. We're going to take the input and the output values, and we're going to construct some points, and then we're going to sketch the graph based on the points. So this one again is a linear function. The reason it's a linear function is because it's got a power of 1 there on the x, and that's just the definition of a linear function. We're not going to chat too much about the types of function, but we will mention them again later. So that's going to make a straight line graph. So we only need 2 points for that one as well. This one's a quadratic function, which makes a U-shaped parabola graph. We'll deal with that one in a second. But in principle, what we're going to do here is we're going to construct a table, and this would work for theoretically for any function. And in the table, we're going to have an x value, and then we're going to have an f of x value. But the f of x value is basically on the graph going to be the y value. So f of x and y are interchangeable when you're thinking about the graph of a function. So we take the x, we put it into the function, and we get some number. So we put 2 in here, we got 6 out. That 6 is the f of 2 value, but in terms of switching it over to the graph, we call that the y value. So we're plotting the inputs along here on the horizontal axis, and we're plotting the outputs on the vertical axis. And that's just how the graphs work. So if we choose a couple of points here, so let's say we choose x at -3, and then we'll just choose +3 as well to see what happens. So if we put -3 into there, so f of -3, -3 times 2, -6, minus 2 is -8. Okay, so that's our first pair, of coordinates. Put 3 into there to get f of 3. 2 times 3 is 6, minus 2 is 4. So all that we're really going to do now then is just pair these guys up. Because it's a linear function, we only need 2 points, so that those 2 pairs are going to be good enough. And we'll just go ahead and plot those on and then draw the graph. But I should really emphasize at this point that it's only because it's a linear function that we need 2 points. If it's something more complex like this guy, we might need to build up more points in the table to get a better picture of the graph. So we'll just go ahead and mark these on. So -3, -8. So -3, -8, that's going to be down, say, there somewhere. And then 3, 4, so 3 along and 4 up. That's going to be maybe like there somewhere. And then we'll just draw a line between those, which just goes like that. So that is a graph. Well, that's meant to be a straight line. It's a bit curvy, but that is theoretically the graph of that function. So what does that tell us? Well, it depends on what type of function it is as to what you're looking for. In terms of a straight line, because they're just lines, the things that we focus on are the gradient, the steepness of the line. We focus on the position of the line based on this point here. And I'm starting to wander a little bit into straight line kind of theory there. But basically the point is, once you've got the graph, once you've got the sketch, that starts to tell you things about the function. So different functions have got different properties that we're interested in. If your function was like this, you might be interested in these turning points, which are key points on a curve type function. So hopefully that lays down the principle. We're just making x, y paired coordinates by using the input and output values of the function. When you move up to something more complicated like this guy here, it can be more difficult to make sure that you get enough of a spread in the points that they're going to be useful for drawing the graph. And what I mean by that is just by looking at the algebra, I don't know where that graph is going to be exactly on the xy axis. So if the graph ends up being over here, this is a curved graph that goes like a U shape. If it's over here, but I choose to look at points over here, I'm going to miss out on maybe some of the key points on the graph. So it's not always easy to judge that. So a good way to do it is to maybe take a wider spread of points. And sometimes you just got to experiment. But the truth is, if you ever want to sketch a graph here in the modern world, we're not going to be plotting points. We're going to use some kind of app on our phone or like an online graphing tool, but it's still good to be able to do it the old school way, because this is kind of the whole point of your understanding. So I'm just going to call this f of x this time, but it's f of x or y. These are kind of interchangeable, and we're just going to put in some values. So let's maybe go for quite a wide spread. Let's go -10, -5, 0, 5, and 10. I've got no idea how these are going to come out, but we'll see what this tells us about the graph. So we're going to put these in here. So let's start with 0. That's a nice easy one. 0, 0, -3. That gives us -3. We'll go for 10. 10 squared is 100, so it's going to be 200. Minus 10 is 190. 187. Positive 187 for that one. So a slightly awkward number to deal with. Slightly high number. Looking at this one, -10, so -10 squared is also positive 100, and times 2 is going to be positive 200, minus 10 is going to be adding 10, so that's 210, minus 3 is plus 210. and 3. I'm doing those calculations at speed. If I've gone wrong, then I apologise, but I think that's correct. Checking this one, so 5 squared is 25, times 2 is 50, minus 8 is 42. And then for minus 5, that's going to be minus 5 squared, which is also positive 25. That's 50 minus 5, 55 minus 2, that's going to be 52, I think. So basically these are bigger numbers, but that's okay, because when we come to draw our graph, we can just basically put on a scale which is representative of the types of numbers we've got. So you don't always have to go like 1, 2, 3. You can go 10, 20, 30. You can even go 50, 100, 150. It just depends. So looking at our x values, we're ranging between 10 and minus 10. So let's maybe say that minus 10 is like there. And then let's say that 10 is over there. And ranging here up and down the way, the y values is quite a wide spread. So we go from minus 3, which is just there, to 203. That's quite a big one. So let's just say that 200 is like there. It should be fine. I mean, we're just trying to get a feel for the kind of overall sense of the graph, which means that 100 would be like there. And we can just say that minus 3 is like there somewhere, okay? I mean, it's just a rough kind of sketch. So what we're going to do now then is plot on the key points. So remember that these are pairs, right? So this guy here forms a pair. They all form pairs. So minus 10, 203. Minus 10, 203. That's up close to the 200. So that's going to be there. Minus 5, 52. So minus 5 is halfway to minus 10. And then 52 is roughly halfway to the 100. So it's going to be around there. 0 minus 3, that's the turning point, the lowest point down there. 5 and then 42, so 5 along, 42 is going to be somewhere in around there. And then 10, 187. So 187 is going to be over about there somewhere, okay? So I said a moment ago this is a turning point. I think actually just looking at the numbers now, that's not quite right. So these x squared quadratic functions, they always make a parabola graph. So a U-shaped graph that either goes like that or it goes like that. That's something that's good to know. And we're going to chat in a moment about the general shape of some function types. This one, if the numbers were perfectly symmetrical around the y-axis, then that might be the turning point, like this lowest point here. I think the way the numbers have come out is slightly more over to this side. So I think the graph's going to turn maybe around here. But these points look really good because we expect this function type to make a parabola, like roughly a U-shape. So that's not bad. I mean, I've just plotted that fairly roughly. It's come out, I mean, roughly like a parabola. So the process though is the important thing. What we've done is we've put some values into the function, we've got the corresponding output values, we've paired them up, plotted some points, enough points to get a feel for the general shape of the graph. If I wanted to be more accurate now, I could go back and maybe use some different numbers, because I know roughly now where to focus. This is my attention here, like where the graph turns. That is the main point of interest on a parabola graph. So I could focus in my attention and draw something more accurate, but the point was just to make a graph that is of the right shape using this technique. Okay, so there's quite a lot to absorb, but just remember that the key point is that all we're doing is basically plotting some points to get a sense for the overall shape of a graph. And just thinking back to where we started, which was how do we even conceptualize the graph of a function? So hopefully that makes sense now about how we just kind of use this idea of a table to make the pairs of points. So just having a quick think about the different types of functions. So we've seen linear functions in this class, which are straight line graphs. We just saw a quadratic function, which makes a parabola graph, either that way or that way. Higher powers of functions, so the next one, which would be an x cubed term, is a cubic function. They start to get more complicated. So a cubic function looks generally something like that, or it might go the other way like that. And then you start to move up to, for example, a quartic function. These are all examples of a family of functions called polynomials. And there's different families of functions, but a quartic function takes on a bunch of different shapes of graph. It can be something like that, like an M shape, or it can be in different orientations. But basically, once you get into the graphs of functions and gain some experience, you'll know by looking at the algebra what type of function you've got. So if you see x squared, you say, well, that's a quadratic function. They make those U-shaped graphs. If you then plot your graph and it doesn't come out to be a U shape, then something's gone wrong. So it gives you that expectation. The same that a cubic function will generally make a shape something like that. Might not be exactly like that, might be flatter, might be wider. Quartics can be a bit more variable, but something maybe like that. So knowing these general shapes of graph allows you to have that expectation, and it kind of guides you along as you start plotting them. So just a quick recap, you can sketch the graph of a function by making paired coordinate pairs by using the input and output values of a function, and then just plotting enough points that you're able to then get a general shape for the graph. So I hope that makes sense. That's just kind of an overview and starting point for figuring out how to work with the graphs of functions.